Are there any questions before we so today is one of like the important days in terms of the course because it's when we will talk about multiplication of matrices, which is kind of uh, one of the big topics in linear algebra. So before doing that, like let me just remind you quickly something I mentioned briefly last time. So if you have a matrix, the idea is that you can do certain matrix operations with matrices. So the first two are really easy. The first one is just that you can multiply a matrix by a scalar or a number, and you still get a new matrix. So you can multiply a matrix by a scalar. So the idea here is that well, you get a matrix of the same size as the original one, and essentially what you do is you just multiply each individual entry of the matrix by that number. So basically, you multiply each entry, the matrix, by that number, but or by that scalar. So I mean, it's just even easier to explain it with an example. So if you take A to be 2, 1, -5, 0, 3, 4, and just to emphasize this from last time, this would be a 2 times 3 matrix, right? Because 2 rows, 3 columns. So it is 2 by 3 matrix. And say if you wanted to do the matrix 3A, what does that mean? 3A would just mean multiply each entry of the matrix by 3. So you get if 3, -15, 0, 9, 12. Is that making sense? So it's not too right. It's kind of like the easiest thing you could imagine of what that would mean. So, so you get like a matrix of the same size. And besides that, there's no other things like worth mentioning about this. You have to sit here. Yeah, or wherever you want. Any other questions about this? Is that okay? Okay, then the next one is just adding matrices. That one is again not that bad. So how do you add matrices of the same size? So the second operation is adding matrices of the same size. And the idea is that you'll get a new matrix of the same size as these two you started with, and basically you just add like the corresponding entries. So you add up, you get a matrix, you get a new matrix of the same size as those you started with as the ones that you are adding. And basically you just do the addition individually. So you add each entry, you add the corresponding entries of the matrix. So again, just to do like a quick example, if A had been like 1, 2, -1, 6, and B had been 0, 1, 2, 3, like just like some random numbers for each matrix. Either each is 2 by 2, so you can add them. The addition should be a new 2 by 2 matrix, and it would just be like again the easiest thing that you could think about. So 1 plus 0 is just 1, 2 plus 1, 2 plus 1 is 3, then -1 plus 2 is 1, and 6 plus 3 is 9. So that's what should come up to be. Is that okay? Is that making sense? And like, I mean, you could like imagine like subtracting matrices. What does that mean? Well, you just subtract the corresponding entries, right? So I mean, so really, it's like a special case of these two because A minus B is like A plus -1 times B. If you want to be like too too careful. I mean, like you can relate it to these two previous cases, but again, when it comes to multiplying by a number or like adding or subtracting, it is basically what you would have thought about doing if maybe you hadn't you're starting to think this for the first time. What's a little bit tricky, and again, that's kind of like the thing that makes linear algebra more interesting is how you should multiply matrices. What should that correspond to? Like for example, like you could come up like say, well, these are 2 by 2 matrices. Maybe multiplication should just be like multiply the corresponding entries, right? Like say something 1 times 0, and then 2 times 1, -1 times 2, 6 times 3, or something like that. That doesn't end up being like a useful thing to do. So multiplying matrices that way, where you just multiply like the individual entries, is not. It just doesn't give you anything interesting. So we have to think about a little bit first of what should the correct formula be. Is that okay? Okay, so we finally get to the important topic for today, which is like the multiplication. And like, I don't want to just like give you right away the formula. Let's just think about a concrete example so that you start getting like an idea of what this is supposed to be like. So I don't know if you remember from last time, we had this mirror matrix. Let's call it, I think we call it M for mirror, right? 0, sorry, it was 1, 0, 0, -1. And the idea was like, if you had started with a vector x, y, right? Like the idea of the mirror was kind of reflecting with respect to the x-axis, if you remember this. So like, again, if you run it through the matrix, this spits out the 1, 0, 0, -1 times xy, which is x -y. Okay, so it was just like do nothing to the first entry and just flip or change the sign of the second entry or multiply by -1, however you want to think about it. Okay. And then if you check the Canvas mini assignment that I gave you for that was I think due today, I asked you to find this switch matrix. That's how I called it. So let's think about that one. The switch or the flip. I don't know how you want. You're switching the entries or like flipping them. So the idea is that whatever this was, like the switch matrix, it will spit out something that just changes like the order of the entries, right? So x now becomes the second entry, the value of x becomes the second entry, and the y now goes into the first entry, right? So we just like turns them around. Anyone remembers the someone thought, but it's
0, 1, 1, 0.
good. Yeah. So it was kind of fun to. I mean, I think it's kind of fun to find these like formulas on your own, like play a little bit with it. But so this should have been 0, 1, 1, 0. times xy. So if you do this multiplication, this product, will give you this, right? So hopefully from last time, like, by now, like this kind of seems natural thing to do, like how to check that this gives you this and this gives you this. Okay, so we have these two processes, right? Taking the reflection and flipping them. Okay, and now to think about what the multiplication should be, it's like you have to think. I'm talking. I think most of you are kind of going into engineering, so these diagrams hopefully like look very natural. So let's just run like one process and then the other, right? Like some sort of like a sequence. So I'll start with x, y, right? I'll mirror it, like I'll reflect it first. So again, when we do that, you get 0, 1, 0, -1 times xy, which was x negative y. And now I'm going to use this vector as the input for the second process, right? So I'm going to switch this one out. And so if you do the switch, you get, again, like it's kind of multiplying it by this matrix. So 0, 1, 1, 0. But now we're multiplying it by the new input, and the input for this process is now x negative y. And so this will give you again, like the switch sends -1, sends the second entry to the first entry, and the first entry to the second entry. Is that making sense? Let me give you a couple of seconds just to digest. Right. So first you mirror it, and then you switch it or flip it, and you end up with this vector, right? And so the cool thing is that you can think of like combining these two processes as a single one. Which we will call like mirror first, then switch. Which like started with x, y, and spits out this vector. And if you think about it, there's actually a matrix that you can, like, think of this as now it's a new question. Like I had started with a vector x, y, and you end up with the vector negative y x. Is there a matrix that describes this? Let's try to find it out. It should be, let's see. I think it would be. So like what I'm trying to say is that if you do, let me write it like this. If you do this matrix times the vector xy, you're getting negative y, right? Remember, like the multiplication was kind of like doing the dot product. So this dot product between these two vectors gives you negative y, and this one dot, this one gives you x. So what I'm trying to say is that doing this matrix and then doing this second matrix can be described by a just like one matrix, which is this one. Okay. Is that kind of like reasonable what I'm trying to say right now? And notice that this matrix, like I mean, it's kind of different from any of these two individual ones, right? It's a new matrix, right? But now here comes the multiplication. The idea is that we will define the multiplication in such a way that this matrix equals the product of this matrix with this matrix, right? Because it's like kind of natural to be like, well, you did this matrix and then this matrix, and that's so like the idea is that you want to define the multiplication, but like our definition should just like give us as a because this one was the switch, and this one was the mirror. So the idea is like the multiplication of matrices will be defined in such a way that the end result of this multiplication is like this combined process. Is that making sense of like what's going on here? So I'll give you a formula that in a couple of minutes, and you'll see that once we have this formula, when we do the product of these two matrices, it does give you this matrix. Okay. Yeah. Oh, why is a mirror here? Like, why do you put it on the right? Because you have to imagine that there's x, y here, and when you if you look at this process, the mirror act was multiplied first by x, y. So this is it's kind of it's kind of like annoying because you're reading it like from right to left in a sense, like first you're multiplying this matrix by the vector, and you got something, and that's the thing that you multiply by this other matrix. So that's why the order, right? The order is kind of maybe the opposite of what you might think, but it's because the vector is on the right side. If that is that making sense? Yeah. So it's right. It is a bit annoying, but you just have to imagine that x. This is saying like do this one first and then do this one, which is again like yeah, it does look like the opposite of how you would read in English or things like that.
Is it kind of like moving from the inside out later?
Right. It's kind of, I mean, it's just that it is the same as composition of functions, right? So if you say g of f of x, again, I don't know how many remember this thing. What does this mean? It means you apply the function f first to x, and then whatever you get, you apply the function g to it, which is kind of like the opposite of how you would read this, right? Because this reads like g followed by f. So you might say, well, it should mean like do g first and then f, but it's kind of the opposite, It is an unfortunate accident that it doesn't match like with our conventions. But I believe in Hebrew or other languages, you do read from right to left. So like perfect. Like now we just like are reading in yeah.
Or is it like just applying one function to another?
It is, I mean, right. Like the thing is like there is a way to like there's really like a way in which we're not doing, but there's like a way in which you could think of this as a function and then this is a function and then this would correspond to like a composition. But for us, it's just like think of it as a direct multiplication. It all kind of like has a happy ending. So both ways to think about it work. But it's just like the way where you think of it as a composition is a little bit more like abstract. So we're trying to do it more down to earth. But secretly, yeah, you could think of it as it really does correspond to some sort of composition, and that's why this works. That making sense, kind of. Yeah, but it does take time a little bit to get used to like how the product is written. But I'm just trying to like we're headed to this formula. Like the first point of this formula is that it will have the property that if you do this matrix and then do this matrix, it kind of like will correspond to the entire process together. Okay, but before I give you the formula, here comes a other important thing that's again what makes the I don't know if you remember, like we have called this matrix S and the mirror matrix M, right? So this would correspond to the product S times M if you prefer like a notation instead of using like actual words. So I'm showing you here what S times M is. Now just to compare this, like because this is like the crucial thing about matrices. What if you run the process in reverse, right? What if we switch and then mirror? What would happen here? So let's try to see how this looks like. So I'm going to start with my vector x, y. Right, I'm going to run it through the pink thing first. So I'm going to switch first. So when you switch, like again, this is was the matrix 0, 1, 1, 0 times xy, which give you yx, right? Like that was the effect of the switching. And now this is the one that I'm going to run through the mirror operation. And so when you do it through the mirror, like it means multiply, it, it means that you were multiplying it by this matrix. Or in other words, like the mirror just like multiplied the second answer by -1. So there could be, like, you could think of creating like a combined process where you switch first and then mirror, right? And so what that means is that if you do like if you put these two together into a single process, you started with xy, and the end result that spits out is y negative x. But the idea is that there's like a matrix that you can find for this process, which would be what? Let's see if we can get it. 0, 1, and -1, 0. Right? If you do 0, 1, -1, 0, times times xy, and y. First, let me see if there are any questions about what I'm doing. Is that making sense? Reasonable? Okay, what's the important thing that you noticed between these two things?
Those who matrix their transpose of each other.
Well, I haven't used the word transpose, but that's more of an accident. It's true, but it's more of an accident. I mean, because of the examples that I'm choosing. Something more important is, yeah.
Multiplication matrices are not conjugated.
Well, the order matter. Like the important observation that I wanted you to see is that this matrix is not equal to that matrix, right? Right, like you could try to find like how are they different, right? But that's not right now what we're concerned with. Like the important thing is like if you do the mirror and then you switch, it's not the same as switching and then mirroring. Which in real life, many things that you do depend on the order and how you do it, right? Like you put your socks first and then your shoes, and it's not the same as putting your shoes and then your socks, right? So there are many operations in the world that does depend in the order in which you do them, but like the idea is like the product of matrices will reflect that fact. So this will correspond to, since you like if this should correspond to 0, 1, 0, 0, -1 times 0, 1, 1, 0, because like again here you were doing the switch first and then the mirroring. Okay, so like what I'm trying to say is that for these particular choices of matrices that I wrote S times M, right? Like summarizing, like the idea is that I want to define multiplication. We have to define multiplication. So that when you do SM, you will get like 0, -1, 1, 0. But if you had done MS, you would get 0, 1, -1. Okay, so like the formula that I'm about to give you, like in 5 or 10 minutes, when you check it, when we do the product, we'll see that we actually do get these two matrices. That making sense? And so I mean, there are not that many things that you have seen before in math, maybe depending on the class that you have taken, where kind of like the order of the operation matters, like when you're doing something algebraic. But this is one of the things where it does matter, and it is again, kind of what gives like linear algebra a lot of its particular flavor compared to other math classes. Let me get any questions about this. But who can hear about Heisenberg's uncertainty principle? Well, so there's right. There's this thing in quantum mechanics where you have like a proton or an electron or things like something like subatomic particle. Like, instead of like you can associate to it like a position and a momentum. Momentum is just mass times velocity, if you haven't heard that before. But in quantum mechanics, you know, when you think about the position of a particle, like if you had like a particle like in one dimension, like imagine like a mass rolling down the x-axis. The position of a particle is just like a number, right? That changes over time. The same with the momentum, it's just like a number because it's mass times velocity. But in quantum mechanics, actually, they become matrices. So like instead of like thinking of the position of a particle as a number, you give associated to it a matrix. And so you have like a matrix for position and a matrix for momentum. And Heisenberg's uncertainty principle basically is that those two matrices, the multiplication between them is not as x, you know, does not commute. Like in the sense that it doesn't matter in which order you multiply them. And that like the interpretation is that it means that you cannot simultaneously measure like the two quantities to arbitrary precision. I mean, there's a little bit more to say about that, but it is like basically this idea that like the uncertainty principle is related to the fact that when you associate matrices to these quantum mechanics things, like the order in which of the matrices, like when you multiply them, it would matter. There are other interesting things, like for example, the matrices have to be of infinite dimension, size infinite, like so it has to be infinite rows, infinite columns. So it kind of makes it a little bit more complicated than what you're used to. But like it is like, you know, it is related to many important things that happen. And this fact that the multiplication does like the order matter in which you do them, does have a lot of consequences. Okay, so let me give you like the formula for the product of the matrices. Actually, like a fun way to find it out. So what should the formula be? I'll show you how it works in 2 by 2, and then I'll give you like the general formula. But it's kind of fun to see what it should be. So, well, I think I don't have to raise that much, right? So imagine I had given you like a matrix A, which will be 2 by 2. So this should be A, B, C, D, like the entries. We don't know what the entries are, right? And I give you a matrix B, which again, I don't know what the entries are. So it should be like E, F, G, H. Hopefully I didn't mess up the order of the letters on the alphabet. So that's like two matrices, two by two matrices, two by two matrices. And I want to give you like a formula for multiplying. So again, if you think of this as a process, you run it through the matrix A first, like the machine A. And when you run it through the matrix A, that means that you're doing A, B, C, D times X, Y. And I don't know if you remember like the formula for this. It was again the dot product between this row and this column vector. So that gives you AX plus BY. And then the dot product between this second row and the column vector, so CX plus BY. Right. So this is like these are the entries of the new vector that we get after we multiply it by A. Right. That making sense of actually. Now I'm going to run this vector, right? Going to run it through the matrix B. So this is what I'm using as input for the matrix B. And like it spits out the product between that matrix and this vector. So it gives you F, E, F, G, H, G, H times this thing. And now we just have to do a little bit of algebra. So again, like the first entry is the dot product between this vector and this vector. So the dot product is E times the first thing plus F. Right, so that's the first entry because like this multiplies the first entry and then F multiplies the second entry and then you just add them together. And then you do dot product between this vector and this vector, so it gives you G times AX plus BY plus H times BX plus BY. That making sense? Any questions about the algebra or like? It looks a little bit messy, you know, a bunch of terms because I gave everything variable names. Like I didn't put like specific numbers, right? So there's no simplification possible, but you kind of have to do it that way in order to like identify what the correct formula should be. Yeah.
2 by 2 matrix.
Well, no, the end result is a vector, right?
Okay.
It's just like it's 2 times 1, right? Because like the first entry of the vector is all this thing, and the second entry of the vector is this thing, right? So it just kind of looks too big, right? So it looks like, oh, maybe it's 2 by 2, but it's really like a vector. Is that making sense?
So the multiplication of both matrices gives a vector.
Well, yes, because I'm multiplying everything by a vector to start with, right? Like the multiplication of 2 matrices will be a matrix, but after you multiply by a vector, it does give you a vector. So it's just that everything is being multiplied by a vector, right? But from here, you'll see we can extract what the multiplication of the matrix. It's kind of like a couple of seconds.
So then now it would be the size of the smallest, like.
Well, I wouldn't say like in terms of size of this like one of like you had like the original input was XY, right? You run it through A and then you run it through B, right? And you get a mess, right? Like this kind of looks like a salad or a word salad. So like we kind of have to rewrite this in a way that's a little bit more useful for our purposes. But right, in terms of size, I'm not sure if I'm answering your question.
That's okay.
You'll see what will happen in a second. Yeah, again, it does look a little bit weird right now because I just gave everything symbols, right? There's no specific numbers. Any other questions? So, okay, here's how you can actually rewrite this in a way that's a little bit more useful. So it's the same vector, I'm just going to rewrite it in a more interesting way. So notice that there are like stuff with X and stuff with X here. So let me factorize that together. So if you factorize that, you know, when you did the product, you get A times E or E times A. Let's see how I'm writing. Okay. And like the stuff that multiplies X here is Z with F, right? Is that okay with everyone agrees that the numbers that are multiplying X in this first row is AE? I mean, it doesn't matter, like AE is the same as EA, like we could also write it that way. I mean, let me write it like in the way in which it appears so that it's maybe. So it's EA plus FC. Okay. Now there's also some stuff that's multiplying Y in the first entry, right? Let me think I need to make this slightly bigger. What's multiplying Y in the first entry? Sorry, EB, right? And what's multiplying Y in the first entry? Also this thing, FD, right? Then let's do the same for the second row, right? There's some stuff multiplying X. So what's the sub multiplying x? Is GA, right? And then HC, right? Plus, and what's the stuff multiplying y in the second entry? It will be GB plus HD. Is that okay? Is that making sense? I don't know. I kind of wrote it in a way that suggests what's about to happen next, right? First number, second number, third number, fourth number. These are going to be the four numbers that appears in the 2 by 2 matrix that corresponds to the multiplication. So the multiplication of the 2 by 2 matrix are just going to be these coefficients. Okay, so what I'm trying to say is that the formula for the multiplication, let me write it down because it's so important that it needs to requires and again, I mean, in a moment, I'll then give you another way to memorize it because the way I'm writing it is a little bit too complicated. But let's see if I can put it here to put it here so that it next appears closer to that. So if like here's the formula. So if again, like you have to matrix it A, B, C, D, and B, which is E, F, G, H. So if you remember like how this was being written, B was the last thing that was done and A was the first one. So what that should mean is that BA is going to be E, F, G, H times A, C, D. And that will correspond to these four numbers that you see here. So this is a master formula, one of the top 5 formulas in the course right here. So well, I don't need to erase that much more. So this is key formula. So let me give you a second to copy it, and then we have to think about how to use it in practice, because right now I'm giving it in a way that's not that useful. Yes.
This first when multiplying matrices, like what the biggest matrix?
I think nothing will go like in practice, like 4 times 4 would be the highest that I would give you. But like if I give you like a 4 times 4, there will be probably many zeros or ones, like you kind of get the idea of how this is supposed to do once up to size 4 by 4, you kind of get most everything is clear. Yeah, so definitely it's not wouldn't give you something where like you would spend a lot of time doing the product. It is bound to many errors because there's just so many multiplications and additions involved. So the more entries I give you, the more like chances are for like a silly arithmetic mistake, and that's not the idea. But yeah, I don't think if I get to something like 4 by 4, like probably that matrix, those matrices would have many zeros somewhere, so that like it's not that complicated. Okay. Okay, so right, like you would say, well, how do you remember this formula, right? It's like there's a way to remember it which is very elegant. So let's try to think about what formula. I mean, in fact, we can continue it here because it's kind of like the way in which you actually remember it. Can anyone think of this first entry as a dot product? Is there a dot product hidden in here? Can anyone identify a dot product? Right, if I take the first row of this matrix, right, and dot it with the first column of this matrix, right, what do you get? EAFC, which is right here. So the first entry is actually dot product of row 1, right, dot column 1, right? Is that making sense? Okay, now that looks better because you just say, okay, it's just like a dot product between row and column, and that's something easier to remember than I just remember these like numbers. And then if you look at this entry, what would that be? It still has like an E and an F. E and F are in the first row, right? But now B and D's are in the second column, right? So this is row 1 dot column 2, right? Let me see if I can put this another color. Okay. And well, you can imagine like the last two entries are kind of the same story, right? So for this one, like you see a G and an H, which are here, second row, and then A and C, which are in the first column. So it's row 2 dot column 1. And then row 2 column 2, right? If you follow this. That's going on. That making sense? So now, okay, this looks better because it's just like, oh, you're really just doing a bunch of dot products, right? Like that's what the matrix multiplication is, bunch of dot products between the rows and the columns, right? So like, if you wanted more like some sort of animation type thing, that's how I think about it. Like think of like taking the first row, you kind of rotate it by 90 degrees, right? You rotate it like 90 degrees and all becomes like a column, and then you do first row with this one, and then first row with this one, and then those are the first two entries, right? And then you take the second row, rotate it, and now it's like that against this, and then that against this, and those are like the last two entries of the matrix, right? So again, this is the key formula in the course, and let's just check that it works for the switch and mirror matrices that I had written before. So So let's do SM. S was 0, 1, 1, 0, right? And M was 1, 0, 0, -1, if I'm not mistaken. So again, like the green rows, like this is, if you want to compare it with the colors I'm using, is something like this. And then the yellow one is here. So again, it's better to do like think of it as an animation. Take the first row, rotate it. So you do 0, 1, dot 1, 0. That's the first entry, right? Then third row, rotate it down to column 2. So it's 0, 1, dot 0, -1. Then second row with first column. So it's 1, 0, dot 1, 0. And then second row with second column is 1, 0, dot 0, -1. Is that making sense? And this, I mean, there are tons of zeros and ones, so these dot products are kind of easy to do. It's 0, -1. And if you go back to your notes, hopefully that's what I wrote when I wrote S times S. Okay. Is there any questions? Well, let me give you a second to copy this. On the other hand, what happens if you do MS? So again, you change the order. It's like 1, 0, 0, -1, and 0, 1, 1, 0. And notice that it's the things that you still keep using the rows of the matrix that you see here first. So like so that kind of gives you like an idea what the product is not expected to be the same in general, because when it's placed in the second location, right, you're looking at its columns, but when you place it in the first spot, like you're looking at its rows, right? So that products just end up being different because like you change your mind about whether you're using the rows or the columns of the matrix depending on where it appears. So if you do this, like again, take the row, rotate it, so it's 1, 0, dot 0, 1. Take the first row, rotate it, do it with the second column, 1, 0, dot 1, 0. Then take the second row, rotate it, do it with the first column, so 0, -1, dot 0, 1. And then take the second row, rotate it, do it with the second column, 0, -1. Okay. And so this one gives you 0, this dot product gives you 1, this dot product gives you -1, and this dot product gives you 0. And hopefully, again, that's kind of looks familiar to what I had written at the beginning, right? So we did finish checking that it recovered what we were expecting that multiplication to be based on the diagrams I had started. And so making sense. And it kind of hopefully gives you like a sense of why this is a useful operation, because literally the matrix multiplication is kind of what it's doing is joining two processes. If you think of a matrix as a process, right? So the multiplication just corresponds to like the union of two matrix processes, and so it wouldn't work if you just multiply the entry 1 with entry 1, entry 2 with entry 2, and things like that. Like it just like doesn't give you anything interesting. Okay.
The top equation, that's that's representing the mirror operation happening first.
Right, yeah, that's, I should say that, like, if you wanted, what does BA mean? It means, that you apply A first to the vector and then then B. Because the vector always comes like written on the right, so BA means, apply A first and then, B. That's, yeah, thanks. That's actually useful to emphasize. It kind of becomes more obvious if I had written like a vector B right next to it. Because now you see like the A for like entering like next to the vector, right? So, so it's like really something like this. And like actually, this notation, if I write it this way, kind of reminds me more of composition, right? Like, and that's why I was saying that this is actually secretly related to some composition. But right, in terms of like, if you thought of the matrices as some sort of physical operation that's happening to the vector, and this notation means like you are doing like the operation A first, and then you're doing the operation B, which again is kind of annoying, like because it's not how you would read it usually. But once you remember to write the vector next to it, it looks less weird, right? Is that okay? Okay, so let's see. I have to give you a bunch of warnings of things that will go wrong with this matrix multiplication before giving you maybe like the general formula. It's kind of useful to like have like some warnings before like, yeah, telling you what it looks in general. So yeah, let's talk about some more. Things that will go wrong if you're not careful. So, well, the first one, the most obvious that I have been saying, A times B is not the same as B times A, right? So that one should go, like hopefully by now it's kind of clear that you should. It's not that sometimes it can be the same. I'm not saying that it's always that you get something different. It's just like in general, you cannot assume that it will give you the same result. Like certain, if you play around with the numbers, some certain coincidences do happen. But yeah, so it's not always the same because it can occur. So it's not always the same. It's not always equal to B. I mean, if you want to say this in a fancy language, you say that matrix multiplication does not commute. That's kind of like the mathematical way of saying this. So matrix multiplication. So again, like we already have some examples, but let me just put two other matrices in case you want to practice it on your own. Like just so if you took like hopefully this number like end up being fine. So if you do 3, 4, 1, 2, and then you do 3, 4, 1, -1. You can try to check as you know some sort of like exercise if you want. Like AB should give you 13, 8, 5, 2. MBA, if everything went well, it would be 13, 20, 2, 2. Okay. Another thing, again, like just before writing it down, like as an analogy, if you have two numbers, X and Y, and their product is zero, right? You would say, well, the product of two numbers can be zero only when one of the two numbers is zero, right? Like multiplication of two numbers, if it's zero, at least one of them has to be zero. The analog of that, what's the analog of zero for a matrix? It's just like the matrix full of zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0. So what can happen here is that you have a product of two matrices that gives you the zero matrix without either of them being zero, the zero matrix. So let me write it down. So you can have AB equals zero. And by this zero, I mean the matrix full of zeros, okay? Without A or B, A nor B being the zero matrix. Without A nor B being the zero matrix. Okay. So again, like just put in some specific matrices for you to check if you want. This is a good exercise. Try to do all these operations, multiplications on your own. Make sure it works. Making sense. So if, oh, sorry. You could take A to be 1, 1, 1. Matrix full of ones. And B to be 1, 1, negative 1, negative 1. Okay. If you do that, then A times B will give you 0, 0, 0, 0. Okay. And notice that here, neither if I mean, none of these matrices are 0, 0, 0, 0, right? But it's even worse. Like neither of them have like a single zero as their entry, right? Like all their entries are non-zero. And still, when you multiply them, you get something with zero entries are all zero. And in fact, what's even worse, like even maybe you would think, oh, maybe in this case, if you get like 0, 0, 0, 0 in the opposite order, you would also get 0, 0, 0, 0. And no, like, and in fact, and moreover, and also, if you did BA, you would get something non-zero in this case. So like if you were thinking how different can AB and BA be from one another, they can be quite different, right? Because here you're getting a bunch of zeros and here you're getting something which is completely non-zero, right? So this is again just to emphasize how careful you need to be. With these equations. In fact, like we'll see later that the reason why this is happening, like one of the reasons is because neither of these matrices is invertible. But we have to talk about that later. Right. You can also have that AB equals ACB. Right, so if you saw that equation between matrices, like again, if you thought about this like as numbers, right? If you wrote A times B equals A times C, well, provided you knew A is non-zero, right? Like you would kind of cancel both sides by A and you would get that B equals C, right? Again, this will not happen with matrices. You cannot cancel matrices. So you have to, you cannot conclude from this that B equals C. So this does not mean so again, if you take A to be 1, 1, 1, 1, and B to be 1, 1, 0, 0. then A times and C to be 0, 0, 1, 1. Okay. You have those three matrices. You can check that AB equals 1, 1, 1, 1, but that's also going to be A. And again, here notice that B and C are quite different. So we can send some second. Okay, the last warning for now is like, well, again, when you had numbers, if you did x plus y squared, right, what would that be equal? It was equal to x squared plus 2xy plus y squared, right? If you remember, like this sum of squares formula, right? Not true for matrices. So in general, a plus b squared is not a squared plus 2ab plus b squared. But what should that be? And this is like a cool example to, like this is kind of how you find like some of these matrix identities involving multiplication. What should a plus b squared mean? It should be a plus b times a plus b, right? If you fact a plus b squared should be a plus b times a plus b. And how did you do like how in fact is it that you would find the x plus y squared formula? Is you just would have started doing like all the possible multi products, right? So you would do this one with this one, right? That would give you a squared. Then this one with this one gives you ab. Then this one with this one, which gives you ba, right? And then this one with this one gives you b squared, right? And so the thing is like with numbers, since ab equals ba, then you get the two ab's, right? But in general, like you cannot say ab equals ba, so that's the actual thing that you can conclude. The best you can conclude.
In this case, could you technically add the matrices separately?
Oh, well, right, like after you do like after you do like the individual products, like you just add them together too. Like you would compute AB, like if I had given you concrete matrices, right? You do the product AB, and then you do the product BA, and then just add them up. And that's what it is. And then you would also add it to A squared and B squared to get like the value. I mean, probably in that case, you might as well just add them first and then squared. It involves less operations. It's kind of useful just to have like the theoretical formula. Like sometimes in practice, once you have like specific numbers, it's less useful, you know, because if I give you, yeah. But like in theory, right, if you don't know at least one of the values of the matrices or whatever, this is how you would do it. And also you can think about, well, what's the, let's see. Like there's another, well, maybe not like a warning, but like there was this identity, right, like x plus y times x minus y equals x squared minus y squared, which you may remember. Difference of squares formula. Let's try to see what would that look like. So you could do like, what happens if you do a plus b times a minus b? Again, it's kind of a with a gives you a squared. A with minus b gives you minus ab. And then B with A gives you plus BA. And then B with minus B gives you minus B squared. Right? So again, it boils down to the fact that you don't know that the BA equals AB, that you can cancel these things in the middle. Yeah.
You can only square a matrix if it's a square matrix.
Oh, well, I have to, yes, basically, although I have to give you like, right now I'm thinking of all of these as being square matrices. But yeah, I have to tell you like how to multiply in general matrices. But right, if you're going to square matrices, like you do need them to be square. So even like it's even worse, like it could fail to be defined, right? If you had like started with rectangular matrices, you cannot even multiply them together or something like that. But I'm just saying, like whenever this word ends up making sense, the correct formula would not be the one that you know. You have to remember that there's now these like terms involving AB and BA that you cannot simplify any further. Is that making sense? Any other questions? Okay, so now just to give you like the general formula, and with that we can finish for today. So let me give you the general formula for the multiplication, and well, let me start with an example, and then I'll give you the general formula. So here's an example. Of matrices which are not squared. So imagine that I had given you so this is 2 by 3, right? So I'm about to tell you a formula that you could use to multiply this matrix by another matrix, right? If you think about what you should put here, right? Like the idea is like the same concept should apply. So you want to take the dot product between this row and the column that appears here, right? So since this row has 3 entries, right? That this column better have 3 entries. That means that it has 3 rows. So in fact, like you should put a 3 here. And then so like what I'm trying to say is that like the matrix multiplication will be well defined whenever these two things match. Because then the number of entries here match with the number of columns, and like I mean with the number of entries in the column, so you can do their dot product. And then like what you put in here is completely random. So let me put like let me do it 3 by 4 just to show you that it doesn't have to coincide with this number, right? Like the outer ones kind of can be completely independent of one another. What you do requires the inner ones to agree. And just to do something easy, okay, so I need 3 entries, 1, 0, 1. Negative 1, 1, 0, and then 0, 0. I'm going to be a little bit like bunch of zeros. Okay. And they will get reabsorbed, and you'll get like a 2 by 4. Like you'll see why in a second. So it's like this one with that, with this one, this one with this one, this one with this one, this one with this one. So let me see if I at least dot 1, 0, 1. And at least I will use some different color for the rest. 1, 0, negative 1. Dot second column, negative 1, 1, 0. Then 1, 0, negative 1. Dot 0, 0, 1. And then 1, 0, negative 1. dot the last column, which is 0, 0, 1. And then for the last one, like it's kind of the same, right? 2, 1, 2, so 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, and then you put like the columns of this one. So it's 0, 1, 1, negative 1, 1, 0, 0, 0, 1, and 0, 0, 1. So not too bad in terms of dot product, but like bound again, so many of the multiplications that you have to do, so it's bound to get a couple of errors. So when you do this one you get 1, 1, negative 1, you get 0. When you do this one, you get negative 1. I think. When you do this dot product, you should get this one goes away, this one goes away. One goes negative 1. And then you got 0. 1. It wasn't too bad. And then when you do this one, you get 2 plus 2, which is 4. And when you do this one, you get negative 2 plus 1. Right. So you get negative 1. When you do the dot product, you get 2. And when you do this last dot product, you get 2 again. So hopefully this is what the matrix multiplication comes. That making sense? And notice that if you have reverse the order, that you wouldn't even be able to multiply that. Okay, so just to if you reverse the order, this is 3 times 4, and this one would have been 2 times 3. The problem is that now you cannot do the dot product between this row and this column, right? They have different sizes, so you're stuck, you stop. So this one can't even be done. Is that making sense? It takes some time to get used to it. But just to give you like this, but like if you think about it as a bunch of dot products, it's less confusing. So so like here's like the general formula, finally. So what would it, so here's like the general formula. So if you had if you wanted to do BA, where this was like an M times N matrix, what you need is A to be N times something else, so it can be whatever other number you want. So they have to coincide, and this will be an M times L matrix. Okay. So since this is M times N, that means that they have M rows. So you can call this like row 1, row 2, up to row M. So these are like the M rows of B. And A, it has L columns. This notation is kind of useful. So like column 1, column 2, up to column L. So these are like the L columns of A. And so the matrix that you get here is like what we have been doing, row 1 with column 1, row 1 with column 2, until you get to row M with column L. So that's what goes in the first row of this product matrix. And then you keep going Like you do row 2 with column 1, row 2 with column 2, until you get to row 2, column L. And finally, depending on how big your matrices are, you do row M with column 1, row M with column 2, and then row M with column L. So like the important thing to remember for a matrix multiplication is that you're using the rows of the factor that appears to the left and the columns of the factor that appears on the right. That's it. If you remember that, then you do the bunch of dot products, and then you. Etc. So yeah, now so I'm saying this is like an important day for the class because this is one of the most important operations. I had mentioned this mirror site. I'll make it public today and upload like a slightly longer assignment for you to have like a week to work on. And then you just upload your solutions to that mirror Canvas site. But it will be a little bit more interesting the mini quizzes I have been giving you because now we do have a little. Now that we have matrix multiplication, we can actually do certain interesting things. Yeah.
In the top right corner, why is it row N? Not
Oh,
row one?
good. Excellent. Good detection. Yes. Perfect. You save the formula for the matrix multiplication. Everything else is fine. Yeah, everything else is good. Thank you. Right, like no one will remember this formula. In practice, you just think of this diagram, right, or something like that. But if you want to like it written down, it's like that. So okay, I'll see you next week. Remember, I have like office hours in case someone wants to show up. But if not, yeah, I'll send you some announcements in a couple of hours tomorrow morning. That later. Yeah, okay. So.
Yeah.
Let me end my meeting.